Hello and welcome to the Analog Devices Precision Digital Isolation Technology training videos on the fundamentals of isolated gate drivers. This video is the fifth in the series and will focus on protection features in gate drivers. To keep switching losses to a minimum, the power devices in an application should quickly transition from the on to the off state and vice versa. In high-power converters, this results in large dVdt and didt during switching transitions. Consider the typical half-bridge topology with IGBTs. The low-side switch is shown more elaborately, indicating the internal gate-to-collector capacitance, CGC, which is the Miller capacitance. The low-side switch is turned off before turning on the high side of the device. During high-side turn-on, the VCE of the low side changes from 0 to some bus voltage value. The high slew rate on VCE causes current to flow through CGC, which is given as I is equal to CGC multiplied by dVCE dt. This induces a voltage spike at the gate of the power switch, and this is known as Miller injection. If the threshold voltage of the power switch is exceeded, then there could be a parasitic turn-on of the low-side device, causing shoot-through and possible damage. A similar gate-to-drain capacitance, CGD, is present in Mosfets, including SiC and GaN. Even though the value of CGD in wide bandgap devices may be lower, the Miller effect is still a big consideration due to faster edge rate. The slew rate on the rising VCE of the low-side switch may cause parasitic turn-on. Keeping the same slew rates at VCE and to minimize the chance of parasitic turn-on of the device, an additional MOSFET can be placed in the turn-off path. During turn-off, this provides a low impedance path for the current due to the dV/dt transition. This Miller clamp MOSFET tries to keep the power device gate connected to ground during the off time. The gate voltage is kept below the threshold as seen in the figure on the right. The gate driver may have an integrated Miller switch, and as soon as the gate voltage of the power device falls below an internal threshold, the internal logic will turn on the Miller clamp switch. The pull-down current capability of the Miller clamp MOSFET determines the current that can pass through the low impedance path. Another consideration is the placement of the Miller clamp MOSFET. Since the inductance and thus the impedance in the turn-off path is affected by its location. Another way to mitigate the effects of Miller injection is to use a negative gate voltage. This maintains the voltage injection due to Miller capacitance below the device threshold. The figure on the right shows the gate voltage being kept below the threshold when using a negative supply. And thus, even without a separate low impedance path, we can prevent parasitic turn-on. As shown in the figure on the left, some gate drivers inherently support a bipolar supply, and these can be easily used for mitigating Miller injection by bringing the gate-to-source voltage negative during turn-off. But for drivers which do not support a negative supply, bipolar supply operation can still be obtained using a Zener diode to set either the negative or positive voltage. Either method can be used to offset the emitter terminal of the IGBT with respect to the gate driver's ground terminal. In a half-bridge setup, both the switches can never be on at the same time, or else there will be shoot-through. During normal operation, the current will flow through either of the switches and through other components in the circuit for some duration, and through the other switch during the remaining duration of the switching cycle. But bad wiring or overload conditions, either between gate and device or on the power leg, may result in higher than normal current in the system. A short circuit occurs when a current higher than the rated value starts passing through the power switch. In this state, current may reach a damaging level. Short circuits can occur due to detachment of wires. IGBTs and SiC Mosfets have a limited capability to withstand current based on their thermal capacity. Excessive currents cause a large amount of heat dissipation in the die, leading to failure. Thus, a protection circuit needs to be designed based on current level and the withstand time period of the device. This circuit will ensure that the power device is turned off before damage. IGBTs have marked desaturation, also called desat characteristics. In power applications, the IGBT is operated in its saturation region. From the IV curve of the IGBT, we consider the condition of when VCE is increasing, that the IGBT is not in the saturation region. A desat mechanism is used that relies on detecting the collector-to-emitter voltage during a fault and can help protect the device. The SiC MOSFET IV curve is different from that of IGBT. SiC devices are MOSFET, and hence do not go into desaturation. Even then, the IV curve of the SiC MOSFET is such that there is no flat desaturation like in IGBTs. But to ensure transition from IGBT to SiC, and for ease of adaptability for customers, protection circuit for SiC devices may still be referred to as desaturation detection. The various regions of operation are shown for both the technologies. This illustrates the difference in the region of operation for the two devices. This is more about the naming convention as well, since the saturation region of the IGBT is analogous to the ohmic or triode region of the MOSFET. There are two typical methods to detect a fault on a SiC device. The current shunt-based method, shown here, can be used for SiC devices due to their IV curve, but it adds extra losses to the system. Most customers prefer a DSAT-type short-circuit protection, commonly called SCP, as the mechanism for silicon carbide. The DSAT detection circuit is integrated in some of the ADI gate drivers as shown. At the beginning of every switching cycle, drain voltage is still transitioning. Switch B1 needs to be turned on in this duration, known as the masking time, to prevent the DSAT comparator from responding. If the masking time is not present, DSAT would generate a false positive before the drain voltage reaches its on-state voltage. The DSAT circuit is effective when the driver output is high and the power switch is on. The figure shows some more details of the internal circuit of one of ADI's isolated gate drivers with an integrated desaturation protection having a DSAT threshold of 9 volts. In the figure, an external resistor, or current, is used to increase the charging current for the DSAT capacitor, in addition to an internal current source. A power diode with its cathode connected to the drain of the IGBT keeps the high voltage from the drive circuitry. When the input signal is low, the IGBT is off, and the voltage across the IGBT's collector and emitter, VCE, is greater than 9 volts, since it blocks a high voltage. At this time, the internal DSAT switch is on and keeps the DSAT pin and blanking capacitor, CDSAT, voltage at ground, and the internal current source is off. During the high duration of the input signal, the IGBT is turned on and there is minimal voltage at VCE. After the masking time, the internal DSAT switch is turned off and the capacitor is allowed to charge to VCE. In case VCE increases above 9 volts and the IGBT tries to come out of the saturation region, a DSAT event, the capacitor voltage increases towards VCE. When CDSAT voltage rises above the 9 volts typical threshold, the internal DSAT threshold is exceeded and the part enters a failure state, and the driver turns off while gradually pulling the gate low. In this design example, we will look at sizing the blanking capacitor, CDSAT. This capacitor sets the blanking time, T-blank, for DSAT detection to be less than the IGBT short-circuit withstand time. Since only the blanking time can be easily modified, CDSAT should be sized such that the capacitor charges to the DSAT threshold voltage to turn the switch off much before TSC. A blanking capacitor CDSAT without an additional external pull-up resistor is charged linearly with an internal precision current source. From the capacitor IV relation, we know that INT equals CDSAT multiplied by the rate of change of voltage over time. In other words, dV divided by dt. This can be written as T-blank equals CDSAT times the internal DSAT threshold voltage divided by the value of the internal current source. To protect the switch, the blanking time needs to be less than difference between short-circuit withstand and the masking time, T-mask. For conservative designs, the fault reporting time, T-report, could also be considered, but a design will still be protected if the reporting time is not included. Hence, rearranging the capacitor equation and keeping the blanking time to meet the timing considerations, we get the CDSAT value. IGBT manufacturers often have a short-circuit rating in the 2 to 10 microsecond range, and thus CDSAT is chosen to provide T-blank accordingly. Choosing a higher value of CDSAT improves noise immunity, and thus we can choose a larger capacitor while adding an external pull-up resistor for increasing the capacitor charging current and still be within spec for the blanking time. The new figure on the right shows the gate driver output being pulled low as the driver enters a soft shutdown mechanism when the DSAT pin voltage exceeds the threshold. Other signals, such as the fault and the driver input, are also labeled. Analog Devices has many digital isolators that provide trusted safety and data integrity. To learn more, please watch the next in our Precision Digital Isolation video training series on the fundamentals of isolated gate drivers. Click on the link below or visit analog.com/iCoupler.